Okay, so we in last video we just introduced the soft support vector machine. So the solution will give us omega, and this gives us decision boundary like this one. But this so far we only talk about this decision boundary is only linear. For example, if we have the 2D feature space, this is just a line. If we in the higher space, we have a higher flat plane. But is there any way we can introduce like a nonlinear case, like a nonlinear support decision boundary? That's what I'm gonna talk next. So the question is how to introduce the nonlinear decision boundary. Actually, once we solve the linear case, we can introduce nonlinear reality by introducing the more features. The idea is very similar to the linear regression. Linear regression doesn't mean you can only fit the linear line, right? You can fit the quadratic, cubic, linear, so very curved nonlinear patterns can be obtained from the linear model. So similar case is here, same as here. So we can introduce nonlinear reality, make the nonlinear features. That fits, that lift points into higher dimensional space. And in the higher dimensional space, it's a linear case. And when we project to the lower feature space, it's gonna give us a linear, nonlinear classifier. So, okay, so that's the idea. Maybe next I give you one example. Is the first example, the parabolic lifting map. Okay, so this function based on the current features, suppose you can think about this is a two-dimensional case. You can think D is two dimension. And then we can introduce one more dimension, D plus 1, by introducing the length of the vector. For example, we have the vector x1, x2, which equals to the vector itself, and we also add one more dimension by the length of the vector. Okay, so here, for example, if D equals to 2, so this function is just we are moving x1, x2, right? And which gives us the first two dimension we have keep same, so x1, x2, and the last dimension we just add the length square. So we give the x1 square plus x2 square. So by doing this, we can introduce we lift. So this means we lift the points into the higher dimensional space. So here I'll give you one example. For example, here we have the two-dimensional case, and we have each point we have two coordinates, right? x1, x2, okay, and then we can lift this two in a parabola sphere, so which means we give the third coordinates, okay, to be the length square. So this is called a phi space. Okay, so in other words, we add one new feature, the length x squared. Even though the new feature is just a function of other input features, it gives us the linear classifier more power. For example, now we can find a classifier, the hyperplane is here, right? Suppose this is our classifier, which can be perfectly classify the blue and the red ones. Actually, in the lower dimensional case, we can only find the linear classifier, which is line. There's no line can perfectly classify these two cases, right? But in the higher dimensional case, we lift it, and we have the hyperplane. This is our decision boundary H. Okay, and after we find and this is our decision boundary, and this decision boundary, when we project to the 2D dimensional case, this gives us this decision boundary. Decision boundary in 2 dimension. So even though this is linear in the higher space, but in the lower dimensional case, this is give us a circle classification boundary. So this is, by doing this, we can introduce the nonlinear decision boundary. Okay. Actually, there is a theorem. So now let's talk about the parabolic lifting map. There is some famous theory behind this simple trick. So theorem, okay. So which means phi, if we apply this parabolic lifting map to each data point x1, phi xn. If in the higher dimensional case is linearly separable, if and only if. So this means if and only if. Okay. If and only if x1 in the original space, x1, xn are separable by a hypersphere. Actually, the proof is very simple, but the idea is even so. In this case, we have very perfect circle, but a lot of cases we may not have the perfect circle. We could have the our decision boundary in the higher dimensional case could be like this, right? And we could have the eclipsed shape. So in this case, we could have this eclipsed shape decision boundary to classify those two cases. Actually, the proof is very simple. Maybe I can sketch the proof here. Consider hypersphere. in RD with center C. And the radians are rho. Let's use rho. X is inside if and only if the distance in the original space, the distance between X and the center of the sphere is less than or equals to rho square. This is equivalent to say we can expand this vector, so this can be written as x, the norm x square, minus 2c dot product with x plus c square. That's then rho square. Actually, we can rewrite this. We can rewrite this as a vector format. So 2 times c transpose 1, scalar 1, and x with the norm x square is less than, we can minus this to the other side. So rho square minus c square. In other words, we have the, let me write down one more step. Minus rho square minus c. Maybe we can write down into the standardized form. So plus c square minus rho square less than 0. Okay, so this is our weight vector omega, right? And this is our feature, transformed feature x, right? So this is our omega x. You can think this is x plus alpha. So this is our alpha less than 0. So we make a decision bound. This is our decision function, and the decision boundary is equal to 0. So which means which proves this theorem. Okay, I think that's maybe we can continue in next video.